Now we're going to go from spherical to rectangular, then we'll do the other way around. In this spherical equation, we're going to begin by multiplying both sides by the row. When we do that, the left-hand side will be a row squared, row times row, and then the right side will be a 2 row cosine phi. Now, just to be sure that you understand, we can do this as long as the row is not a 0. So we're taking the origin out of the picture by multiplying both sides by row. That's okay. It may work itself out in the end, but we'll just make that note that row can't be a 0 because we just multiplied by a row. However, at this point, the row squared from here is x squared plus y squared plus z squared, and the row cosine phi is just a z. Which, as you can see, we could write in a little bit more standard form as x squared plus y squared plus z squared minus 2z equals 0. And we'll go ahead and write this a little bit more in general form. This z squared minus 2z, we're going to do completing the square on. So z squared minus 2z, if we take half of the 2z, which would be 1, and square it, we need to add a 1 here so that we come out with a z minus 1 in parentheses squared. Well, if we add 1 on the left, we also have to add 1 on the right. So we have an x squared plus y squared plus z minus 1 squared, which we can now see is a sphere with the center at 0, 0, 1. And it has a radius of 1. Now here's the picture of it down in the corner, which I already have loaded. Now we're trying to come out with the spherical equation for this rectangular equation. So I guess what we'll do is just take each of the variables and replace it. Here's the x, which we'll replace with a row sine phi cosine theta. Here's the y, which we will replace with the row sine phi sine theta. Here's the z, which we'll replace with a row cosine phi. So there we have all of the variables replaced. Now that is not a very good form to leave it in, so let's see what we can do. Dang it, almost screwed up trying to get too big a hurry. So there's what we need to do. So when we square this x, we'll have a row squared sine squared phi cosine squared theta. And here we'll have a row squared sine squared phi sine squared theta. And here we'll have a 3 row squared cosine squared phi. On all of these, we can factor out the rho squared. On this one, these two rather, we can factor out the sine squared phi, which would leave the cosine squared theta plus the sine squared theta. We can replace the cosine squared theta plus sine squared theta with a 1. I'll just mark that out. So we end up with the rho squared times the sine squared phi minus 3 cosine squared phi equals 0. So we know from what we did earlier that either the rho squared is equal to 0, which means the origin, the dot at the origin, or the sine squared phi minus the 3 cosine squared phi is equal to 0. Taking this second one, we've got the sine squared phi equals the 3 cosine squared phi. If we divide both sides, that's supposed to be a phi. If we divide both sides by cosine squared phi, we get the tan squared phi equals 3. If we do the square root of both sides, we get the tan of phi, I keep writing a theta, but that's supposed to be a phi, equals plus or minus the square root of 3. Now, the trig is a little tricky here because if you do the arctan of the square root of 3, your calculator gives you the appropriate answer, which would be phi equals pi over 3. If you do the arctan of the negative square root of 3, however, your calculator is going to give you the negative pi over 3. Well, that's not a valid phi angle. Phi has to be between 0 and pi. So we just need the negative pi over 3 back up in quadrant 2. I'll draw it for you. We'll come over here. So here's what we found. Here is a phi of negative pi over 3. The angle over here that matches that is going to be the angle 2 pi over 3. So that's what our answer would look like. Phi equals pi over 3 or phi equals 2 pi over 3, which is going to be a cone, but elliptical shaped.